garter pins, self-locking nuts, lock washers, clip locks, and snap rings. First, let's take a look at safety device method that requires the greatest amount of effort and skill: the use of safety wire. Safety wire comes in a variety of diameters: 20 thousandths, 32 thousandths, 41 thousandths, 51 thousandths, and 57 thousandths. It can be manufactured from stainless steel, zinc-coated steel, and alloy of nickel and copper called Monel, brass, or plain copper. The most common type, the one that every good A&P has in their toolbox, is 32 thousand stainless steel wire. The diameter material used, however, is determined not by what is available, but rather by the type of component on which we find the hardware being safety, and the size of the hole drilled to accommodate the safety wire. For example, it is accepted practice that the safety wire fill at least 75% of the drilled hole. It should not, however, be so tight that it must be forced through the hole. This can damage the wire. For most installations, stainless steel wire is acceptable. To best understand the intricacies of safety wire installations, we should first examine a typical double twist job involving two bolts being safety to each other. You will need a pair of safety glasses, the proper diameter safety wire, a pair of duck-bill pliers, a set of diagonal cutters, a 6-inch ruler for measuring the safety wire's twist per inch, and a pair of snap ring pliers. Further along in this demonstration, a rubber mallet and a torque wrench will be used when installing garter pins. Take an approximate measure of the distance between the bolt heads using the wire as a ruler. Cut a length of wire approximately 3 1/2 times the distance measured. Choose which of the bolt heads will be the starting port and insert the wire in such a way that it loops around the bolt head and creates 2 strands of equal length. For right-hand threaded fasteners, which includes 99% of all hardware, the final wire installation should form a rough letter Z when viewed from above. The concept is that if one bolt were to vibrate loose, it would tend to tighten the second bolt, thus preventing the loosening hardware from backing out. Begin twisting the 2 strands together in such a way that the strand exiting the drill hole holds the loop portion down. This is important to prevent the loop from vibrating up over the bolt head and causing the entire installation to loosen. Gauge the distance between the 2 bolt heads and begin twisting the 2 strands together clockwise. Be careful not to twist the wire so tight that it stretches. This will cause stress in the wire and it may crack under vibration. Approximately 8 twists per inch is the accepted technique. The twist per inch can be checked by laying a 6-inch ruler alongside the safety wire's twist and looking at the average twist per inch. The wire should be taut but not stretched. Insert 1 strand and loop the other around the second bolt head. On the side of the second bolt head, opposite of where our wire first entered, begin twisting the 2 strands together as shown. The loop portion should be under the strand that extends through the hole. This pigtail helps tighten and secure the safety wire installation. Cut the pigtail so that a minimum of 3 complete twists remain. Remember to wear your safety glasses. Turn the pigtail around or under so that it does not present a sharp edge. This razor sharp end can cause injury to the next person working on the aircraft. The final product should look like this. It is also acceptable to safety wire 3 bolts or screws together as shown here. Just remember to produce a Z pattern between each set of items. Another method that can be used in certain situations is the single wire technique. In this procedure, a single strand of safety wire is run through a series of closely spaced screws. Note that if one screw begins to loosen, it tends to pull both adjacent screws in a tightening direction. This method cannot be used unless permitted by the manufacturer. Safety wire is also used to secure a single fastener to a tie point, as shown in this illustration. Regardless of which method is employed, safety wire should never be reused. A second type of hardware safety device is the cotter pin, or cotter key. Cotter pins are utilized to safety castellated nuts, clevis pins, and shafts. Although not as difficult to install as safety wire, cotter pins require some practice in order to be effective. In order to do the job properly, you should wear safety glasses, obtain the correct size cotter pin, and use a set of diagonal cutters to accomplish the work. A pair of duckbill pliers and a rubber mallet may be used to help bend the prongs. As with the use of safety wire, selection of the correct diameter and length of cotter pin is essential. When referencing our aircraft technician specification handbook, we see that cotter pins come in two distinct categories. AN380s, which are manufactured from low carbon steel, and AN381s, which are made from corrosion resistant steel. The type used will depend upon the material being safety. If the bolt, nut, pin, or shaft is constructed of steel or steel alloy, AN380 cotter pins are fine. If another type of material is employed, then corrosion-resistant steel AN381 will be needed. In addition to material, cotter pins are identified according to diameter and length. The prongs may be even, uneven, or bent. Diameters are measured in 32nds of an inch. Lengths are classified in 1/4 of an inch for AN380s and 1/16 of an inch for AN381s. For example, an AN part number for a corrosion-resistant steel cotter pin that has a 1/8 of an inch diameter and a 7/8 of an inch long is AN381-4-14. Let's examine a typical castellated nut safety job to learn the proper techniques for cotter pin installation. First, select a diameter pin that will fill the bolt holes as completely as possible without forcing it. The bolt hole and the openings in the castellated nut must align. If they do not, there are methods that can be used to bring them into alignment. For instance, torque values are given within a range, such as 325 to 375 inch-pounds. Tighten the nut to the lower part of the range and increase torque until the holes align. Be careful to never exceed the prescribed torque value. If this does not work, switch to another nut. If neither of these methods works, change the thickness of the washer used. Next, insert the cotter pin into the drilled bolt hole until stopped by the head of the pin. It should be installed with the head positioned as shown. Bend the one prong up and across the end of the bolt using a pair of duckbill pliers. For cotter pins, trim prong ends now can be snugged around the exterior of the nut by lightly tapping them with the rubber mallet. Bend the remaining prong in the opposite direction with the duckbill pliers. If the cotter pin moves too freely in its hole, vibration may eventually cause it to break. Cotter pins used to secure clevis pins should be installed as shown. Note that each prong of the cotter pin is bent around the circumference of the clevis pin. The next type of safety method to discuss is the self-locking nut. In our lesson dealing with the various types of aircraft hardware, we discussed the identification and uses of self-locking nuts in significant depth. Self-locking nuts, whether they are metal or fiber insert, are installed in the same manner as ordinary nuts. As discussed in our lesson on hardware, fiber insert self-locking nuts should be discarded if they can be run down on the threads by hand. Rather than rehash the entire presentation on self-locking nuts, we will instead go over a list of do's and don'ts involved with the use and installation of these self-safetying devices. 1. Always ensure that at least one full thread of the bolt or stud extends through the end of the nut. 2. Never use a fiber insert nut in an area of high temperature, such as an engine compartment. 3. Always use a flat washer between the self-locking nut and the material being fastened. 4. Don't reuse a self-locking nut that can be run down on the thread by hand unless it was designed to do so. Fiber insert nuts are never designed to be run down by hand. 5. Only use self-locking nuts where they are required. They cannot be used to replace other types of nuts or safety devices. 6. Always use the specified amount of torque, never over-torque or under-torque. A fourth type of hardware safety device is the lock washer. Like the self-locking nut, we discussed the identification and use of lock washers in our class on aircraft hardware. Also, with the self-locking nut, no additional tools are needed other than those already being used for the hardware installation. To review, there are two types of lock washers, spring and tooth. The spring type secures the hardware by providing a tension between the fastener and the material being fastened. The tooth type actually bites into the hardware to secure the installation. Regardless of which type is used, the lock washer must be installed between the nut and the flat washer. It should never be against the material being fastened. This will damage the surface and could initiate corrosion. There are 5 basic don'ts when dealing with lock washers. 1. Don't use them on primary or secondary structures. Use them only where approved. 2. Don't use lock washers where failure would permit the opening of a joint to the airflow. 3. Don't use them where they are subject to frequent removal. 4. Don't use lock washers where they are subject to corrosive conditions. 5. Don't use a lock washer without a flat washer between it and the material being fastened. The next focus of our attention is a small convenient device known as a clip lock or lock clip. The lock clip is used to safety turnbuckles. Its part number is NAS 651. The lock clip can be used in place of safety wire as a means of securing turnbuckles. As can be seen, the use of safety wire to secure a turnbuckle can be complicated. As shown here, 2 clip locks can be utilized to secure a turnbuckle installation. The shortcoming to this type of safety device is that not all turnbuckles are drilled to accommodate them. The undrilled type of turnbuckle must be secured by using safety wire. Installing the clip lock normally involves no additional tool. The final type of safety device discussed in this lesson is the snap ring. Installation of a snap ring usually requires the use of a special set of pliers. Snap rings are manufactured from metal in such a manner that they have a spring-like action. This spring action will hold the snap ring in a groove that is designed to accommodate this particular means of safety. The internal snap ring, as shown here, requires no additional securing mechanism. External snap rings, which are installed on the outer surface of a shaft, may be safety wired, as illustrated. As discussed at the beginning of this lesson, the purpose of using these safety devices is to prevent hardware from loosening due to vibration and becoming foreign objects or debris known as FOD. This is a much greater concern with aircraft and other forms of transportation because the vibration cannot be dampened by contact with a solid or liquid. In flight, the aircraft structure absorbs the vibration. We looked at 6 different means of securing hardware: safety wire, garter pins, self-locking nuts, lock washers, clip locks, and snap rings. Each method must be used only where prescribed by the manufacturer. We are not free to substitute one technique for another just for the sake of convenience. This is not only illegal, but extremely dangerous. For answers to specific questions about hardware safety methods, ask a certified A&P technician, refer to the Aircraft Technician Specification Handbook, or contact us at repairs@pia.aero for a prompt reply.